So the next talk is Wesley. He will tell us about automatic inference of enclave placement in LLVM.
Yeah, so thank you. Yeah, my name is Wesley Nuzzo. I will be presenting our work. It's a work in progress on automatic inference of enclave placement in the LLVM compiler. So I would like to start by talking about how we enforce confidentiality of secret information in our secure applications. So in this example, I have a secure banking application that is outputting, is logging transactions, that is outputting some information to a public log that's publicly visible, and then some information is secret information that's being output to the private log and is secure from observers. So here's an example of what that code might look like. We don't necessarily need to understand this in detail, but the basic idea here is that I have the ability to check the balance of an account. I can deposit money into an account, and I can withdraw from the account. And each of these transactions is logging something, so I'm using the log public function to output information to that public log, and I'm using log private to output information to the private log. And the information that I'm trying to keep secret here is just the balances and the amounts. And then the rest of the information we're treating as public information. So the first thing that I can do to try to keep this information secret is I can use information flow control, and I can label my information as either public or private, and we would do this for the entire program. For example, that's what it looks like in the check balance function. And then the type system will ensure that we're not violating those guarantees and that we're not outputting anything publicly that should be output privately. And so this is good, but it does not give us any protection against an attacker that is not bound by IFC. So if we're linking to a library or we're running alongside other programs on the same system that have access to the memory, they can violate these guarantees. So in this example, I have a hardware level attacker who has figured out that we are storing our secret balances array at a particular location in memory. He's able to create a pointer to that location in memory and is able to read from that memory and then output it to the public log and thereby violate our guarantees. So we want to prevent this from happening. And so one way to prevent this from happening is with trusted execution environments. So trusted execution environments are a hardware technique that gives us the ability to create enclaves. And enclaves are secure, protected regions of code so that code that's not running inside the enclave cannot access enclave data. So when our attacker has figured out where our balances array is, and he tries to read from that array, the enclave system, the attacker is running outside of the enclave, and the enclave prevents him from being able to access that information. And so if we combine TEs with information flow control, we get applications that are secure by construction against these kinds of attackers. And so that's sort of where the state of the art is, but there's still a problem here. And the problem is that what we would like to do is take this code protected with IFC and place it inside of an enclave to protect an attacker, but we can't put the entire program inside of an enclave. The main reason for this is that enclaves have a limited amount of memory. So if I try to put the entire program into an enclave, I'll run out of memory. The other problem is enclaves take a certain amount of time to set up and tear down. So, and more instructions means it takes longer to set up. So that may not necessarily be efficient. So what we need to do is we need to partition our enclave or our code into enclave code that will run inside the enclave and then host code that can run outside of the enclave. And so here's an example of how we might partition the code. I'm going to show partitioning the data. In practice, we partition the data and we also partition the instructions. So this is just for demonstration. And so in this example, I'm choosing to place, I'm placing balances and amount. Both of those are secret, so those have to go inside the enclave. I'm also placing UID, which is public. I'm placing that inside an enclave. It's OK to do that, and in some cases, it might be more efficient. And then I'm placing num users in the host. So this is one example of a partition that we can do that will give us the protection that we want. And there are other partitions that are possible. One of the dangers of trying to partition our code by hand is that we can make a mistake. So in this example, I've placed balances in the host outside of the enclave, so we no longer are being protected from attackers. So that's a problem, and we want to avoid that. So we don't want to partition manually, we want to partition automatically. We've already labeled the information that we want to be secret because we've used the IFC, we've labeled things as public and private. So we want to be able to just automatically choose a partition that guarantees that the private information goes inside of an enclave. And ideally we want to try to choose an optimal partition. So what we do is we treat this as a compilation problem. We start with a source language that only has information flow control and does not have enclaves. And then our target language is an information that enforces those guarantees with trusted execution environments. And so in the process of compiling from the source language and the target language, we have to do this enclave inference. So up until now, there's no practical compiler that can confer enclave placement. And so we are doing this in LLVM. And one of the benefits of, so LLVM is, again, a practical compiler where we can actually use this to compile real programs. And one of the benefits of using LLVM as well is that if you have any source language that has IFC, if you can lower it to our version of IR that's extended with security types, then we can compile it the rest of the way. And we can also potentially, we're starting by targeting SGX, but we can also potentially target other types of enclaves such as ARM Trust Zone. So those are our two high-level contributions. Are first, the automatic inference of enclave placement in LLVM IR, and then second, that we then compile that IR all the way down to SGX using OpenEnclave, and the final application runs on the actual SGX hardware. Right. So to elaborate a little bit more on the first point, there's one of the interesting challenges of getting this to work at LLVM is we're working much more closer to the assembly level. So we have to handle IFC a little bit differently because we have implicit flows in information flow control. And the way that you detect that in a high-level language is different than in LLVM, where our control flow is handled through jump instructions. So we can have all kinds of arbitrary control flows that are not possible in high-level languages. So we have a specific analysis of the control flow graph to determine that information. So then, again, just to elaborate on the sort of steps of that first contribution there, again, automatic inference of enclave placement. So first we have a pen and paper formalization of LLVM with, again, both our source language is SIR, so it's LLVM IR extended with information flow control. And then our target language is Siren, which is LLVM and IFC and enclaves. And then, again, we have that static branch analysis, and we have the compilation from SIR to Siren. So here's an example of what SIR looks like. This is basically what what LLVM IR looks like, but we've added those public and privates. Those are our information flow control security labels. Tau here is either, again, an integer. Essentially, it's an integer, a Boolean, or it's a pointer to another type. And so if you look at, like, for example, the load instruction, so tau private is the label on X. That's the, we're loading from a pointer Y and we're loading it into a variable X. So tau private would be the label on X, and then tau star private, the second part, is the label on Y, or the type of Y. This is what Siren looks like, or rather, the Siren, we start with SIR, and then we're adding a mode value to pointers that indicates whether the pointer is inside of an enclave or not. And then we are adding a few new instructions, such as enclave enter and enclave exit, to handle entering and exiting an enclave. So this is an example, again, so this is an example of what Siren is. Again, that mu y there is the value on y that indicates whether it's in an enclave or not. And then enclave enter and enclave exit, they kind of work like a function call. So if I'm in the middle of a block, I call enclave enter. I enter into an enclave and I sort of jump to this enclave block. And then I potentially go through a few more enclave blocks, and then I reach my final block, and I reach an enclave exit. And when I do the enclave exit, I return back to the original place where I called the enclave enter font. So our goal here, again, is to start with a secure SIR program, and we will compile it to a secure siren program. And again, we're starting with enclave agnostic, and then we infer enclaves in the process. So in order to do this, we need to start with making sure that our SIR program is secure. So our definition of security here is non-interference, that public outputs are not influenced by private inputs. And we can start enforcing this with type system. So this is sort of an example of what a typing rule looks like. For this load instruction, I kind of explained what again, we're loading from pointer y into the pointer x. And then this rule here basically creates the requirement that the label on y flows to the label on x. So if I'm trying to load if I'm loading from a private value to a public value, we'll reject that. And so that gives us some protection, but this alone is not sufficient. And again, the reason for that is the implicit flows. So this is an example of code that has an implicit flow. We are doing a branch on a secret instruction, and then we're outputting something different depending on whether the secret is true or false. This doesn't violate the typing rule that we've shown before, so in order to solve this problem, we need a PC label on each of these blocks that tracks the secrecy of the context, tracks whether that context depends on secret information. So the simplest way to go about doing this would be to just say that if a block is reachable from that private branch condition, then it would have to get a PC of private. And so that looks like this, right? The first block is public, and then block 1 and block 2 are private because they're immediately reachable from that secret condition, from that branch instruction. And then the branch instruction also reaches block 3, so we would label block 3 as being private. And this is enough to give us the guarantee of non-interference. Now, if we say that in a private block we can't do anything that's publicly visible, then we now get our protection. But this is a little bit stricter than we actually need. So if we look at block 3, if we take the left branch, we end up in block 3, and if we take the right path, we end up in block 3. So either way, we end up in block 3. And so we're not actually leaking any information by the fact that we're in block 3. So, and so in CFG terms, block 3 post-dominates block 0. So this is a little bit similar to a concept. So the fact that we do this means that we can lower the label from public to private, or from private to public. So this is similar to a concept in typed assembly where something called a junction point. And you can do a similar, we've recently found out there's other work that does something similar when handling IFC in typed assembly. But yeah, when this happens, we can lower the label from private to public. And this is much better. It gives us, more the ability to sort of lower the PC label back down while still giving us the non-interference guarantee. And so now we modify that. This is the final typing rule. We have the PC label in there, and we have this constraint that says that the PC has to flow to the variable that we're assigning to. And that's how we get our guarantee. And then, we're still working on the theorem of the enforcement of security, but the theorem would be that well-typed SIR programs are secure. So now we have a well-typed SIR program, and we want to compile it to our secure siren program. And again, we need to bring enclaves into it by doing so. So the key insight here is that we are transforming, we are turning this into a constraint optimization problem. Like I said, we have the hard constraints here that we want to make sure that private variables get inside an enclave. We also want to choose what we think is an optimal solution. So that's where our soft constraints come in, is we want to try to choose an optimal partition. So we do this in 2 steps. First, there's the constraint generation, and then we give that to an SMT solver, and that will give us the final enclave assignment. So first, with the constraint generation, this is what the constraint generation looks like. We start with a well-typed SIR. we start with a well-typed SIR instruction, and then we will compile that to three things. First, a siren instruction. Second, the execution mode of the instruction that indicates whether it will run in or outside of the enclave. And finally, the constraints on it. And so the constraints encode. So this constraint, for example, creates the requirement that the pointer mode is inside of an enclave if the pointer is private. And then this constraint here says that the execution mode of the instruction has to be inside of an enclave if the pointer mode is inside of an enclave. So those are the constraints. And then now that we've generated the constraints, we need to solve the constraints. So we give that to an SMT solver. And then we can try to optimize for a variety of different criteria that we think might give a most efficient solution. So we can try to have as few instructions in an enclave as possible, or we can try to minimize the number of times that we're entering and exiting an enclave, or we can try to have more enclaves or fewer enclaves. We can also try to minimize the lifetime of an enclave. And then the final output, again, will be a partition that satisfies those constraints, and we use that to generate the final siren code. And again, the theorem is in progress, but the theorem starts with that a well-typed siren program, SIR program translates to a well-typed siren program, and then that the well-typed siren programs are secure. And then finally, just a few details on the implementation. When we're implementing this in LLVM IR, when we're adding security types and constraints, we represent that in LLVM using metadata. So it's very flexible. And then the constraint optimization, we represent using SMT. We represent the constraints using SMT-lib2 constraints, and we give those constraints to the Z3 solver, which gives us the final partition. And then with the final compilation to SGX, we use OpenEnclave SDK to generate the final compilation. And so we have this working for a basic Hello World example, and we're working on more complicated programs. And so that concludes my presentation. I'm going to open up to any questions.
Brian? Thanks for the talk. I haven't seen a lot of work with LLVM in this context. I'm curious if there's any overlap with the techniques that people in the multi-party computation world use. Because there you're also sometimes starting with an information flow program and then trying to split it into pieces with some explicit cost of going back and forth.
Yeah, I'm not sure. So like distributed systems or something?
Yeah, there was the viaduct work from Cornell at one point.
I mean, there's definitely a benefit to if you have mutually distrusting components, you can have them running in different enclaves. Because if you have code running in different enclaves, code in one enclave can't access what's in another enclave. Right. So that's a benefit of having enclaves. But that's one way to use enclaves.
Okay.
Yeah, so if there's not other questions, I can ask one. How do you get Z3 to also deal with these soft constraints?
I mean, I'm basically thinking of that as those are sort of the things that we're optimizing for. I don't know if that was clear.
I mean, by default, I think Z3 just tells you SAT and SAT, and for SAT gives you a model, but is there a way to call Z3 that optimizes things?
Yeah, so we give a cost function. I can add on to that, sorry, Wesley. We actually encode the cost function as a SAT and unsat, and then that gives back an answer from Z3. So yeah, there's a workaround in that, yeah.
Okay. I'm not sure we're allowed to go to the next talk until 6 minutes or something. So we can also take a break, but if there's more questions, we can definitely take them.
I was having a hard time getting this presentation to be quick enough when I was practicing, and now it went really fast.
Yeah, thanks for the talk. I was wondering, So like your like public variables can live like outside the enclave, right?
Yeah. The public variables can go in an enclave or outside the enclave.
Right. So can like a malicious OS like change the public variables so that when the program in the enclave use those values is gonna trick basically the program in the enclave to leak?
Yeah, I mean, so you're asking basically about the capabilities of the attacker. So we're basically, we're assuming that we're compiling a trusted program, and then like potentially linking to an attacker that again is running at the hardware level and isn't protected by IFC. So, you know, if someone is messing with your code and is messing with the labels, then you don't get that protection. But if we're dealing with an attacker, if we're just linking to a library, they can't change the labels or the stuff that we compiled.
No, that's fine.
Also,
sorry, go ahead.
Yeah. Well, also, like, enclaves have a attestation process where you can, so I think I don't understand it fully, but like I think you know, you would have like a hash of the program. So if someone's like messing with your program after it's completely compiled, it wouldn't be able to run in the enclave.
So I guess like my question is like, how do you ensure the integrity of the public variable that may live outside the enclave might not like end up breaking your?
I mean, so my thinking is that you would start with the source language, and then you would compile it all the way without any chance for an attacker to intervene with that. And then if you're linking to a public library or something, the final SGX code doesn't actually have security types at all. We rely entirely on the enclaves to provide that protection.
Yeah, but your compiler might decide to place part.
Yeah. If your compiler can't be trusted, then.
No. I'm using your compiler. Your compiler decides to put some memory that the program needs outside the enclave. Now this memory can be corrupted by the attacker. How does how does this like come up in your proofs or like in your
part of the guarantee of information flow control?
Okay.
I don't know if I have a better answer to that. I'm sorry.
So I guess the question is more about integrity than about secrecy, right?
So we are only considering passive attacker at the moment. So integrity is active attacker, so which would be the next step. But you're exactly right. So all our guarantees are up in the air. Yeah.
Hi, thanks for the talk. Just going back to like the previous question about the Z3 encoding and the cost or the optimization, I guess. I guess this might be too technical, but I'm wondering like how do you do that cost analysis? Like do you statically know, you know, how expensive placing certain stuff in an enclave is, or like how do you know without running the program? I guess.
Yeah, I mean the idea is that we can kind of tune those optimization criteria according to what we think is the most effective. So we can start with something, and then if we, you know, we can play around with those optimization criteria to get what we think is the most efficient.
Okay, so like it's like an experimental type of thing.
I mean, that's sort of part of the idea is like there isn't necessarily one objectively correct answer. It might not be the same for all like hardware, right? So there's some freedom to sort of explore.
Cool, thanks.
There's still time for one last question.
So maybe this is a more broad question, but kind of can you answer maybe like what's the general cost of like switching to an enclave when you're running a program? Like, you know, you're talking about a couple 100 milliseconds to switch, and then like also secondary question, you kind of mentioned at the beginning like not a lot of languages really support this like enclave stuff at like a high level. Is my interpretation of you saying that correct?
Mike, still use it while you answer. Yes.
There's no automatic compiler. There's no practical compiler like LLVM that's doing this kind of enclave inference. There are theoretical compilers that are doing it, but doing it in practice, this is the first. The idea is to take that and do it in practice.
Okay, so now we need to switch. Let's thank Wesley again.